Institute. So I'd like to welcome up Julita Carbalam. Sorry, beg your pardon. Loreto. I seem to have the order mixed up. My apologies. I have Loreto Mateu. She's the department head of integrated circuits in the systems department for Fraunhofer Institute for Integrated Circuits. And her title is Energy Efficient AI Hardware, Neuromorphic Circuits and Tools. Thank you, Loreto.
Thank you for Okay, so I will first in my talk give you a motivation why we need HAI hardware, and then I will just jump into which are the challenges of designing energy efficient and low latency application-specific integrated circuits for neural networks. So if we want to bring AI to the edge, devices to IoT, to devices to sensors, so really where the data is generated and collected. We need also to bring there the AI hardware that can compute the AI algorithms and not do it anymore on the cloud. So which are the advantages of bringing AI to the edge? So we will have low latency because we are not sending all the raw data that we are generating to the cloud anymore. So the AI algorithm will run locally. Then we will have a higher energy efficiency, right? Because we are computing again locally and we are not sending all this raw data to the cloud. And this is done mainly in a wireless way that even consumes more. And then we have as a third advantage the privacy. So because the data remains where it's generated and we don't send it to the cloud. So these are the three main advantages, and there are really use cases and applications that need this low latency and high energy efficiency. And when I'm talking here about low latency and high energy efficiency, I'm talking about microseconds, and I'm talking about nanojoules per inference. So we heard before cloud computing, high-performance computing, about hundreds of watts, thousands of watts. So I'm really talking here about milliwatts or microwatts, right? So this open also the new possibilities, new use cases. And really to master this low latency and high energy efficiency, since we are dealing with the end of Moore's law, we cannot rely anymore in conventional von Neumann architectures. We really need here to go for brain-inspired architectures, so non-von Neumann architectures, right? Where we don't have this bottleneck, this von Neumann bottleneck between the memory block and the computation engine. So we really need to compute close to the memory or in the memory to achieve these numbers. So for now on, I will be talking about, to you about inference accelerator ASICs for neural networks. And what are the objectives that these inference accelerator ASICs need to achieve in order to be successful in the market, and also in order to cover a broad range of use cases. So first, they need to be designed and fabricated in established qualified semiconductor processes, because no company, right, it's going to buy an ASIC of a non-qualified CMOS process. Then we really need this ultra-low energy consumption per inference. So while we run one inference, we need to be really energy efficient, and we need to be really fast. And then another objective to achieve is a small area. Why? Because this will lead to a low price of your ASIC. And then the fifth objective is to make a configurable and scalable multi-core architecture, because on this way you can cover several use cases with the same architecture. Okay, so how we can achieve this? So in my opinion, there are 6 enablers for neuromorphic computing, 6 areas of expertise that you have and need to master in order to reach the objectives I talked to you before. The first one is system architecture. We heard about this before. Alan explained this. So there are architectures for artificial neural networks. There are architectures for spiking neural networks. You can do, for example, a single core architecture, a multi-core architecture. You can have a multi-core architecture with a network on chip for neural networks, or for spiking neural networks, you can also have a multi-core architecture with mesh routing, and you can do this in a digital way, in an analog way, in a mixed signal way. And then you have the circuits, right? Because you have an architecture, but you also need the circuit designers, and you need low-power circuits. And for the synapses, for the neurons, for the activation functions, and so on. And then you have another expertise that's related with algorithms. So we need to fit this neural network model into an ASIC. So we faced often with the challenge of compressing the algorithm. Sometimes the algorithm, the neural network model that it's giving to us, is too big to be fitted on the ASIC, and we need to compress it. And then we need also software tools. We need quantization training tools, hardware-aware training tools. We need a mapper and a compiler to be able to map this neural network into our hardware. And we have also the physical devices, right? We do the integrated circuit design with process design kits, with the CMOS transistors. We need to choose the right technology node, so that we really have a high energy efficiency. And then another topic that's very broad are embedded non-volatile memories in order to decrease the leakage that this ASIC can have. This can help, of course, in some use cases, and there are many flavors of embedded non-volatile memories, RAMs, MRAMs, PCMs, ferroelectric FETs. So for now on, I will focus on the architectures, the circuits, and the software tools, but just that you are aware, you need all these expertises, and you need really to combine them, so you cannot focus in one and forget the others. So at Fraunhofer IIS, we are doing a mixed signal ANN ASIC, inference accelerator ASIC with analog in-memory computing. So a lot of companies and research institutes and universities are doing this in a digital way. I would like to explain you why we are doing this in an analog way. And it's not only because we want to give nice challenges to our analog IC designers, it has also other reasons. So here you can see the equation of the output of a neuron. And you see here, it's a multiply and accumulate operation mainly. So if we can accelerate this and do it in a very energy efficient way, the whole ASIC will be energy efficient, and it will be also fast. So how can we do this? Can we do this in an analog way? So it's called in-memory computing. It means the weights are stored there. so are this transistor with the resistor there. These are the weights. And the X are the inputs, right, of your neuron. So you multiply each input with the resistance, and with Ohm's law, you get a current flowing there. And you do the same for the second input, X2, and by Kirchhoff's law, you are adding the currents, right? So on this way, you can really also do the nonlinear activation function on an analog way, or do it in a digital way, but what's important is to do the Mach operation in an analog way. Why? You see here, you can profit from high parallelism and from high computation speed. And since there is no data movement, because you are computing on the memory, then you get the energy efficiency on top. Okay, but we saw the advantages, so let's see which are the disadvantages of this analog in memory computing. So here you can see the distribution, so a measured distribution of the weights on these analog circuits. So we target 7 different values for the weights, and you can see here, okay, some of them match, but there is a distribution, so there is no exact matching between our measured value and the target value. So how we deal with this? Because anyway, we need an accurate NN computation, right? So no one is going to buy our ASIC if we have a very bad accuracy, right? So for dealing with this, we profit for what we call hardware-aware training. So we don't do only quantization-aware training, right, where we quantize the weights so that we have a low memory footprint and then again, better energy efficiency. We do also what we call fault-aware quantization training. So we give a variance to the weight, and we train with this variance in order to get a robust neural network model that can deal with the variance of the hardware. And then the third box here related with hardware-aware training is we have also seen that we need to explore the model, so in order to exchange the model also with the end users. So the second tool that is very important is the mapping tool. So you have a neural network model, and you have, for example, like here, a multi-core ASIC with 6 different cores. And here we see an example of a voice activity detection network mapping, where we have 7 different layers that are mapped in these 6 different cores. So the mapping for in-memory computing can follow different strategies, so reduction of data movement, maximum utilization of hardware resources, and depending on the strategy you follow, this will have a huge impact on the key performance indicators of your ASIC. So it will have a huge impact on through output, on latency, on energy consumption. So you need to be very careful, and it can happen sometimes. You have a very good architecture, very good circuits, but if your mapper is not so good, you will get not such great results, right? So, and then I want just maybe to comment about benchmarking. So there are a lot of inference accelerator ASICs that compares themselves with others based on the TOPS per watt, so on the operations per second and watt that they can perform. Be very careful with this, because it's not so easy to find out how this number came up, yeah? And I prefer really to don't use this number and focus on the use case, right? So for this, of course, we need a benchmarking framework, And it will be necessary to have a network architecture search engine that really explores all hardware capabilities and at the end gives us the model that better can perform on a certain hardware, right? And when we get different models that are the best model that gives you the best KPIs on a certain hardware, only then can you do a fair comparison. But please do always this comparison based on the use cases. And then I go to the conclusions. We need a tool change and for doing really hardware-software co-design. So we talk about these 6 enablers. So we need architecture, circuits, we need software tools, and we need this hardware-software co-design and this tool change for the design, and we need it also for the end users. And then another point that I want to bring your attention to is that we need accurate NN computation at circuit level. So there are many papers that talk about TOPS per watt that they outperform, but they never said, is this a typical simulation? Did they do corner simulation, mismatch simulation? Is this circuit really robust or not, right? And as I said before, be careful with benchmarking and do use case-based benchmarking. Thank you very much. So here you have my contact information.
Thank you, Loreto. Very interesting. Do we have any questions from the audience? Yep. Yeah, come to the mic if you can, yeah.
It's more of a question about energy efficiency again. So you had the TOPS per watt, and there are metrics that we're trying to use in data centers, for example. It's called the ITEE, for example, which is an ISO metric. But when you actually look at the units, it's actually top per joule.
Yes.
So it's the work that needs to be done. And we always get stuck in this problem of the time it takes to compute. So is it critical? Is time critical in a lot of applications? Because then, you know, when you go out and buy an automobile, a vehicle, you say, how efficient is the vehicle? The person selling you the vehicle should say, well, how do you drive? Because that's the important thing, yeah. So it was more of an issue around how we deal with this energy efficiency metrics, or how we get to a good energy efficiency metric.
Yeah, so that's why I brought the use case benchmarking. So we think the energy per inference, yeah, and the latency per inference, these are good metrics here, yeah, to compare use cases.
Yeah.
But not the TOPS per watt, because you don't know. No, so normally they just give you the maximum number of operations that theoretically this hardware can perform, and then they divide by some middle value of energy from some use case, yeah, and right, so that's not good for comparison. So I recommend the energy per inference and the latency per inference.
Any other questions? No? I have one. So, yeah, this is a very interesting area. I've got actually a couple of questions, but the first one is, in this analog world, you went through all the details and you can just see the tremendous energy benefits from the potential of that. But unfortunately, we have to interface with the digital world.
Yes.
So do you take into account the ADCs and the DAC power as well?
We take this into account. So we develop an architecture that doesn't need the DACs. So they are integrated in this in-memory computing part, but we need the ADCs. So we design, for example, SAR ADCs because they are low energy, right? So 9-bit SAR ADC, that's the interface at the moment between the analog and the digital world. Yeah, and we take the energy into account. Yeah.
And I think the other thing that you basically covered at the beginning of the presentation is you're focused on the really low energy edge.
Yes.
And the way I like to look at this is actually we need to start thinking of the whole as the computer. So from the cloud to the near edge to the intelligent IoT edge, which I guess is really, you're working in those two.
Yes.
But when you partition your application, you want to decide, can I push it to the edge so I'm not burning all that power taking it to the cloud? So it's very linked to, these are...
Yeah, so we even have seen some applications in which the bottleneck, it's not the energy, but it's the latency.
Yes.
So where the FPGAs and CPUs can really not manage the computation with the small amount of time that it's needed. And so there are two aspects here, that can profit from this architecture. So one is the energy, of course, but the other aspect is the latency. So there are some radar lidar applications in which you have such amount of data, and you need to compute the next one really close, really fast, right? Yeah. So you need to be really fast.
Right. I tend to find that if you reduce latency, you tend to reduce energy as well.
Yes, of course.
You do get one with the other. Any more questions?
So, two questions. One is, do you have already preliminary data about
Yeah, thanks.
Okay, so do you already have preliminary data about the energy efficiency compared, let's say, to traditional NVIDIA systems? That is one question, and the other question is, I like the approach to go on the application question, right? So how efficient do you solve this application? Are there already standards out how to do this in the community? Where are we there at this point?
Yeah. So for the first question, so once we compare a use case, a neural network, on an NVIDIA FPGA, I don't remember the model, and on our hardware, but it was a theoretical comparison because for this architecture, for this multi-core architecture, we received the ASICs yesterday, so we didn't measure them, so it's based on the simulation, on cadence simulations, and we were like 350 times on the energy efficient side better, right? And the second question, if there are some standards and so on. So there is this TinyML community where they have like neural network reference models, and they try to benchmark different hardwares while you use the same neural network model. But I think this is also a little bit misleading, right? Because if you need to really do this for a huge amount or some different neural network models, because you can have a hardware accelerator for example, for the ResNet model. No, it will outperform when you do the ResNet model, and it will not do anything when you run there another NN model, right? So, but you can look on TinyML. So there is a community there trying to do this benchmarking.
Okay, thank you.
We are good on time, so we can take one more question, maybe.
It doesn't work, I think.
This one? Yeah. This solution is also for edge computing, as I understand correctly. Or
sorry, again?
Is this these accelerators are also for edge computing, or mainly for edge computing?
So they are meant for, I would say, more for IoT sensors, but HAI, on the edge.
On the edge, I mean.
Yes.
How do you handle the environmental changes on the edge? Because when you are using analog part, I think there is big role of environmental properties, mainly temperature, changing the temperature. How do you handle this problem?
We do corner simulations, of course, and we define our temperature corners, so with minus 40 up to 85. So we simulate and we see if the design is inside the corners, no? If the specifications are inside the corners. So we run inferences. So for example, 1,000 inferences on cadence, and we see, okay, do we get the same accuracy than with our hardware, our training model? And if it's the case, we know the circuit it's good.
Oh, okay, thank you.
Thank you, Loreto. That was very good.
Thank you.
I'd now